Hello beautiful girls and smart boys. Welcome again to this very journey of the theory of sets. We were playing with operations on sets by our last lecture and we discussed some very beautiful results wherein alternatively we can use the basic operation definition in some other forms. Those results basically were wherein some we understood with the form of Venn diagrams and the others we did formal proof about it. Well, that was also based on the very understanding of what these operations are actually. What were those results? Let us quickly recapitulate because they are going to be used in today's lectures as well. The very first result we did gave us an alternative form of the very operation of difference of two sets. So if I have two distinct sets A and B and I am interested in the third set which is formed with the help of A and B, which is A minus B, in that case obtaining A minus B in a traditional sense has an alternate form, which is either you do the traditional way of obtaining A minus B or you basically take the first set as it is, the second set take its complement and take their very intersection. Finding the common elements between A and B complement are the same elements which are collected when you subtract B from A. And therefore, you have another alternate definition of A minus B, which is A intersection B complement. Going to the very second result gave us a very alternative form of B minus A. Similarly, just like removing B from A had an alternative form, exactly in the same manner, removing A from B has a form of a very similar manner. What is it? Well, you just have to take the first set as it is, second set take its complement, and then you just have to find the common elements between these two sets. Both these sets B minus A and B intersection A complement, A minus B and A intersection B complement are the same sets. Going to our very third observation and result, we had concluded that the set A minus B is actually equal to A provided A intersection B is the empty set, which means if you consider very natural case of A minus B is actually a set which is smaller than A, because you in a very general scenario remove some elements from A which are common to A and B, and therefore the size of A after removing those elements becomes smaller than what it previously was. But suppose there are no common elements. In that case, removing elements from A which are in B, this statement makes no sense, and therefore the size of A minus B remains undisturbed and A comes out to be equal to A minus B. This was a very beautiful result and we proved it both ways round. Coming to the fourth point, we had that A minus B, this particular set where A and B are two distinct sets, when its intersection is taken with set B, what you obtain is an empty set. It's very logical. If you are removing B from A, that means left out members in A minus B are purely of A. No element in A minus B is an element of B, and B has all its elements, and it's common sense that they will not have any elements in common because I am already removing elements of B from A. After this, I told you that taking the union of A minus B with the same set B not just results in a non-empty set but results in a massive set which is A union B. After this, we landed on to the very interesting observation wherein we were given that A is a subset of B. That means A's size is smaller than the size of B. But how can I swap the roles because B is feeling bad? Or maybe A is feeling bad because its size is smaller than the size of B. Well, A wants to make B's size smaller than itself. Generally, this cannot happen. But once you take complement, this thing is true. And this implies that on taking complements, B complement is going to be smaller than A complement. This was the sixth result, which again we had established in the form of visualizing what is going on with the help of Venn diagrams. And then the very last result, application of the operations on the algebra of sets, we had that if I take A minus B union B minus A, okay, this set and the set which is obtained by taking A union B and removing the intersection portion are the same sets. You also know that this A minus B union B minus A is the definition of A del B, which is nothing but the symmetric difference of the two sets. And therefore, you can also say that A del B has an alternative definition, which is A del B is equal to A union B minus A intersection B. Just chuck out the common members between A and B, and what you obtain by doing that from A union B is the symmetric difference of A and B. These results, one getting completed, bring us next to some more interesting results on the operations of sets itself. Mind it, this is the game going on which we are playing with the operations of union, intersection, difference, symmetric difference and complements. Everything of this is a tool that we are going to use in our questionnaire round. And therefore, brace yourselves up, pull up your socks, because next coming with us are some more bunch of results on the operations of sets. What are they? These are some more results which are going to make life easy for us, because they will again give us alternative forms of finding out the very description of sets which are not so direct. Let me introduce you to the very first result. The first result says that if you have a set A and B and C, which are three distinct sets, and suppose I am interested in taking B intersection C. This particular set is basically the members which are sitting inside both B and C. What I want to do is, I want to remove the intersection portion of B and C from A. What am I going to obtain if I do this? Well, B intersection C is a set, A is a set, subtraction of two sets is a set. Therefore, on the right hand side, I am always going to get a set. But how will that set actually look? For that, hold on, because I have the description. That set basically looks like the form wherein this minus sign goes inside B, this minus sign goes inside C, but at the cost of changing the intersection sign from intersection to union. And therefore, it becomes A minus B, A minus C, just like the distributive laws that we had done, and this intersection changes to union. Now, what do you think is the formal proof of this particular claim? For this, let me start an element belonging to the left hand side, and I will have to show that the same element belongs to the right hand side because I am using a fact. What is the fact that I am using? Let me first give you that fact. That fact says that A equals B only when A is contained in B and B is contained in A. This is the very fact that I am going to use in order to show that these two sets are actually the same. Which means firstly I am going to show that my set A is contained in set B, and then I will show my set B is contained in set A, and then conclude that my A is equal to B. What are the A's and B's in our particular result? Here the entire left hand side is acting as one set and the entire right hand side acts as the other set. In order to show that the LHS set is equal to the RHS set, I will have to show that LHS set is contained in the RHS set and RHS set is contained in the LHS set. The very first claim that we are going to show is that the LHS set is contained in the RHS set. Let's start with that. What is it that I have to show? Let's write it so that there is no ambiguity while we are doing the proof. I have to show that A minus B intersection C is contained in A minus B union A minus C. Let me write that. I have to show A minus B intersection C, which is the LHS set, is contained in A minus B union A minus C, the RHS set. How do I show that this set is contained in this set? This means that every element which belongs to LHS set is a member of the RHS set, is what I have to show by the very definition of subsets. Because here that is what I am showing. I am showing the LHS set is a subset of the RHS set. And so I am going to consider an arbitrary element in the LHS set and show that that element which I am picking up from the left hand side set is also a member of the right hand side set. And therefore, because I am going to pick up the arbitrary element, this proof is going to be true for every element of the left hand side set. And therefore, we are going to come to the conclusion that every element of LHS is a member of the RHS, and therefore R to show will be shown. So let me start with an arbitrary element of the left hand side set. Let X be any element belonging to the left hand side set. X is belonging to A minus B intersection C. We know that A minus some set means this bracketed set is being removed from A, and therefore X is an element which definitely is a member of A, but it is definitely not a member of B intersection C because this portion is removed. And now we are having that yes, X belongs to A, but X does not belong to B intersection C, which means X is not a common element of B and C. This is only possible if either X is not a member of B or X is not a member of C. Suppose X is a member of B but not a member of C. In that case, X will not come out to be a member of B intersection C. Also, if X is a member of C and X is not a member of B, even that case X cannot come out to be a member of B intersection C. And therefore, this particular statement can be said that X does not belong to B or X does not belong to C. Even if it does not belong to one of the sets, it is not going to belong to the intersection set. What is the next thing? So we have X belongs to A and X does not belong to B or X does not belong to C. Now read it carefully. X is definitely a member of A. With that, either of the two possibilities hold. That means either X is a member of A and X does not belongs to B is true, or X is a member of A and X is not a member of C. This is true. Either of the two is true. And we know that if X is a member of A and X is not a member of B, where is X actually lying? X is lying in the difference of A and B. Because I am removing B from A, and that is what is written in the words above. Or X belongs to A minus C. You know what is the meaning of or. Either X belongs to this or X belongs to this, which means X belongs to A minus B union A minus C. This is what is the definition of union of two sets. Does this match to the right hand side set that we had? Well, yes. A minus B union A minus C is the set which we are landing at. And because we had started with X being any member of the LHS, we have proved that that same X is a member of the RHS also. This means every member of LHS is also belonging to RHS, and therefore my LHS, which is A minus B intersection C, is very much a subset of A minus B union A minus C. Once we have arrived at this particular conclusion, this is my equation number 1. I am going to present before you the argument wherein I will prove that my right hand side set is a subset of the left hand side set right after this particular thing that you write down all these in your notebooks. Let's see how it makes us whack our brains. The question says there are two events A and B. Basically, two sets or two events distinct make the same sense. A is given to you as a distinct set and B is given to you as another distinct set. Which of the following is simple expression of this entire expression? Let me note this down for you. The expression given to us is A intersection B. This particular set is taken union with A intersection B complement. Remember, we had done 3 expressions in which complement of a set can be written. The second set is A intersection B complement. And the third set is A complement intersection B with the union sign. The question says, what is that set which you are going to obtain once you take the union of this set and this third set? The very fine, refined and easy way to understand this is through Venn diagrams. Let us try and draw Venn diagrams for each of these cases, and then eventually we are going to get what we want. The very first Venn diagram will be related to the first expression A intersection B. All of us know that if A and B are two distinct sets, then how is A intersection B represented? A intersection B is the common portion between A and B. Now this shaded portion here represents A intersection B. I am supposed to take the union of this shaded portion with which set? I have to take it with A intersection B complement. So let us draw another Venn diagram which is going to show us visually what is A intersection B complement. You all know that A intersection B complement means members which are sitting inside A and which are sitting inside B complement. But B complement has members means those members are not sitting inside the set B, and therefore A intersection B complement means all the members of A which are not sitting inside B. Do you remember anything from that? This was the very meaning of the difference of set A minus B. How do you plot or graphically in the form of Venn diagram represent A minus B? From A, remove the intersection, and what you will obtain is this. From the entire A, I have removed the contribution of B, and this yellow shaded portion gives me A minus B, also known as A intersection B complement. In the question, as you can see, A minus B is not written. What is written is A intersection B complement. You should be very thorough with the understanding of what this expression means, because if you get stuck, you won't be able to decode it as A minus B. What is the third expression? Now this shaded portion is again asked to be taken union with the third Venn diagram. What is it? The third Venn diagram is asking us to find out the portion which is represented by A complement intersection B. Now we all know that A complement intersection B can also be written as B intersection A complement. Why did I do that? Because intersection is a commutative operation, and therefore A complement intersection B becomes B intersection A complement. And from this, again, we can conclude just in a similar way that we concluded that A intersection B complement is meaning that B is getting removed from A. Similarly, B intersection A complement means A is getting removed from B. So this turns out to be B minus A. It is now very simple to plot B minus A because we just have to remove the contribution of A from B. And that gives me this particular white shaded portion. This is the portion which has elements which are purely in B, and therefore I have obtained the very third portion which is B minus A. And now we just have to take the union of all three. Union of the intersection with the union of this shaded portion with the union of this shaded portion. Let's see what the resulting Venn diagram is. The Venn diagram that we obtain should have the intersection portion. That means this should be present. The next says this yellow shaded portion should be present. And the third one says this white shaded portion should be present. What is this? Isn't this the collection of all the members which are sitting in either A or B? This is what, my friends, is the very Venn diagram of A union B. This means if I collect all the members in the intersection plus all the members sitting purely in A plus all the members sitting purely in B, I am going to get all the members of A and B including the intersection. Let's see if this option is there in the four options. The first option, A intersection B, no, we don't want that because the answer is A union B. The second option is A union B, and this is the correct option. Option number B among the four options gets to be ticked. You are now supposed to copy this down quickly so that we move on to our very next question. Now, after understanding how, in what all ways can a set's decomposition can be given, this is what it said. This was a very smart way of decomposing a simple set in the form of 3 distinct sets. But what we obtained was the very first set that we learned in the creation of new sets, which was A union B. The next question waiting for us says that if universal set U is the set of 3 natural numbers 1, 2 and 3, set A is of 2 natural numbers 1 and 2. Now this is obvious that my set A is a subset of the universal set, in fact proper subset. Mind it, because 3 is sitting inside U, A does not have 3. Then it is saying, what do you think will be the complement of the power set of A? Here we are asked to find out the complement of the power set of A. Now you, just understand this, I am starting with solution number 2. My A is given to be 1, 2 and my universal set U is given to be 1, 2 and 3. We all know that set A is a proper subset of the universal set, correct? What do you think will be the case between